Hey guys, in this particular video I'm going to be talking about gravitational potential energy. But first let's recall what work is. Recall that work is just equal to the integral of our force vector dot dr. Alright, and let's say that we've got a practical example of, say, a ball resting on the ground, like this. And let's say under the action of several forces, and any amount of forces really, that could be varying with time, the ball's path varies like this. I want to make it as arbitrary as possible. And consequently, the ball ends up in its final location, say, just here. And we're asked to calculate the work done by gravity exclusively. So, in other words, there are definitely other forces acting on this ball in order to make it move in this particular type of strange path. But we wanted to figure out what is the work done by gravity alone. Alright, in order to do this, we need to create an axis. So let's just choose an axis like this. I'm going to choose an axis to be located off in space somewhere around here to make it just as arbitrary as possible. So this is our axis right here. And I'm going to choose Y to be facing above the ground. So our positive Y is directed above the ground. This is very common notation. And as a consequence, X will be facing over here and Z will be facing out of the page. But for the most important part you need to know about this is that Y will always be facing above the ground. That's the notation I'm going to be using for this particular type of problem and many other problems following this. Consequently, our force due to gravity, which we know has a magnitude of mg, let me make that a little bit clearer, is going to be, let me fix that up. Our force due to gravity is going to be directly downwards, and it will have a magnitude of mass times by the acceleration of gravity. So in other words, the force due to gravity will always be negative mg, and it's negative because it's facing away from the positive y direction. Consequently, we can work out what the work due to gravity is now by simply directly subbing it into this formula right here. So let's do that. Recall that the work due to gravity, which I'll call work grav, is equal to the integral of our force vector, which we know is just going to be equal to 0 because there's no component of our force in our x direction. It's going to be minus mg because it's entirely in our negative y direction, and it's going to be 0 in the z component. And that's going to be dotted with our dr, which is just going to be dx in the x direction, dy in the y direction, and dz in the z direction. Alright, consequently we can simplify this a little bit more using our definition of the dot product. And that'll simplify nicely into 0 minus mg dy plus 0. And because this is now just a one-dimensional integral, we can put the limits of integration as y1 to y2. In other words, our starting y position to our final y position. Alright, well we can simplify this even further now. Under the assumption that the mass of the ball remains constant, and under the assumption that gravity remains constant, right, which is actually a somewhat flawed assumption, because gravity will actually slightly change with height, but we're assuming that the height is almost negligible, the height change is almost negligible. The acceleration due to gravity is approximately constant, so we can take it out of the integral sign to leave it with minus mg integral dy from limits y1 to y2. Consequently now we can evaluate this very, very easy integral as, and let me write it down here, work due to gravity in this particular case is equal to minus mg delta y. So it's going to be y2 minus y1 after evaluating the integral. Alright, well let's talk about this real quick. Let me just put a box around this to signify its importance. This is the work done by gravity. Alright, well let's think about this. If y2 is greater than y1, in other words, if there's positive movement upwards, and only upwards, that means that the work done by gravity is negative. Right? And that may seem counterintuitive to you at first, but it really makes sense. I mean, if the ball moves upwards, and the force acting on it is downwards, that means that the work done by gravity is going to be negative. In other words, the work has to be done by something else in order to move it up there. Alright, not only that, but we can continue this a little bit further. Let's define gravitational potential energy, sometimes written as GPE, sometimes written as U, let's define it as mgy, or sometimes written as mgh. Let's define this as that. Consequently now, we can re-express our work done by gravity in a different type of fashion. We can write this now as, let me just put an equal sign here, that's just going to be minus mg y2 plus mg y1. Alright, well this will just be equal to minus gravitational potential energy at our second point, and that's going to be plus our gravitational potential energy at our first point. I don't know why I wrote P there, that should be 2. Alright, consequently, we can write this now as a negative change, our negative change in gravitational potential energy. And you'll see the importance of this in following videos, but for now, the important things to know is the work done by gravity is this, and we're defining gravitational potential energy as this. You'll see where this all ties into conservative and non-conservative forces later, and in the next video I'm going to be defining elastic energy. Thanks, guys.